So, hi everyone. My name is Szymon, and I have the pleasure to host this meeting. My talk is about Hadoop and Storm, which is a great combo for real-time big data systems. And I wanted to start with Hadoop and Storm. So, how many of you know Hadoop, have heard something about Hadoop, wanted to try Hadoop? Some people, great. How many of you have actually written some code that would run on Hadoop? Still some people. Who is running MapReduce jobs every day, or running Hive queries every day, or working with Hadoop every day? No one. Oh, one person. Great. Something new. And what about Storm? How many of you have written something in Storm? Great, one person. Every day or just tutorial? Every day. Awesome. So we'll definitely start with explaining what Hadoop and Storm is. Yeah, this is actually first part of the plan. Hadoop and Storm, then our setup of Hadoop, Storm, and other services around this, and of course the integration of the core base product with big data stack. This will be set up to show you what are we actually calculating with the stack, what kind of projects are we running, how it works, and what did we have to decide while implementing this? How did it work out? We made some great decisions, we made some bad decisions, so maybe some ideas for you what decisions will you have to make when implementing this. Let's start with Hadoop. So Hadoop is, from a really, really high perspective, I would say Hadoop is a kind of operating system for a data center. So let's say you have couple machines that you want to run some programs on. You probably want to run the same program on all of them to gather all the power. To run any program, you probably need an open file system under this to run your code and to store your data. So Hadoop provides this as well. It can provide both a local file system on every single machine and then shared file system. Make sure that if you run a single program on multiple machines, then they all have access to the same data and they can share the access, see each other's changes. Pretty cool thing is Amazon version on Hadoop. So you can run Hadoop cluster in Amazon Cloud, and then you see two file systems. One of them is the HDFS, the other one is S3. So you get one huge file system where you can upload gigabytes and gigabytes of data, and then you get all this computing power. So to run a successful program on multiple machines, you definitely need some kind of resource management. You need to say how much RAM do you have, what slots where are available. You need to monitor the processes running, make sure that if something crashes, then it will get restarted. Make sure that if there is a list of tasks to do, then they will be scheduled in order and run in order. So these are all pieces of Hadoop. This is job tracker and task tracker. And then, as with every operating system, there is a paradigm of programming, the way you're writing programs. So traditionally in Hadoop, there was MapReduce paradigm, which was exactly telling you how do you load the data, how do you load the data, how do you work with the data, how do you transfer the data, and how do you output the data. And this was pretty monogenic. So you would just load gigabytes of data, run all your computations on the data, and output the data, and this would be all. Fortunately, there is second version of Hadoop getting really popular right now, totally production ready, which introduced Yarn. And Yarn is real resource scheduler. So if you want to run any code on a cluster, if you want to run your magic web server, which doesn't have anything to do with processing data, you can take this web server, give it to Yarn. Yarn will say, okay, cool, I have this much RAM, I have this many machines, I can run this server in 50 instances if you want. I can monitor it. If it crashes, I can restart it somewhere else. And you can totally use one huge data center as a single computer. So this sounds really cool, but it has some minuses. Mostly, traditionally, the MapReduce framework was really bulky and really slow. So the idea would be, if you have couple hundred megabytes, couple gigabytes of data, you do this on your local machine and you don't go with Hadoop. If you have terabytes, petabytes, then you don't care about startup time, spin-up time. So every job would take a couple minutes to set up proper monitoring and to prepare everything for you. And then the idea would be you run this once every couple hours or once a day, and you don't, like, nobody is actively waiting, or no paying user is actively waiting for the result. So this is a huge minus. And that's not a problem if you're running, for example, if you're Spotify and you gather logs about who was listening to which song, and then after the day's end, you take all the logs and calculate how much do you have to pay to which vendor, and this happens every night, for example, and takes some time. But it's not that perfect if you want to serve users real-time, clicking on the website and waiting for your data. There is another solution for this, which is called Storm. Storm starts with really similar place. So you have all those machines, and you have heavy calculation problem or lot of data to process, but you want to process them in different way. You have a stream of events, and the entire idea is streaming processing. So an event comes, or a couple events come, and you want to calculate them as fast as possible, deliver the result to someone maybe waiting, maybe you just want to do it fast, and then go with another one. So good analogy would be, for example, email. It's not that fast that you can click and get the result immediately, but if email comes and it takes 20 seconds, 15 seconds, 30 seconds to show you that the email arrived, it's probably not a problem, and this is what happens in most of the services. So the user is kind of indirectly waiting for the results. To get a bit deeper into how Storm works and what it actually provides, let's look at this ugly diagram. So the entire idea of Storm is you have those streams of messages, and then you have multiple programs or calculation units that will process the messages, so eat them and produce more messages and send the next messages to the next programs, and the next programs will consume the messages and send the next messages. In the meantime, for example, going to the database, storing something on disk, sending a message to someone outside the system, sending an email, finishing a report, and finally all the messages will be processed. So the spout is where the entire calculation starts. So for example, email oh, I don't have the cursor. Yeah, so the email arrives, and Spout is responsible for making sure, taking the email from external system, pushing this into Storm, and making sure that every single piece of calculation required to mark this email as completely done is done. If something fails down the road, then it's monitoring the execution and will retry until it's successful. Then those squares called bolts, these are logical programs. So I would say if you're processing emails and counting the emails, then this square would be the code that is actually counting the emails. But inside of it, there will be two instances of this code, because we want to run this with parallelism too. So another thing that Storm gives us is automatic scaling of different pieces of calculation. It's actually monitoring what's the throughput of this piece of code, what's the CPU usage, is it fast enough to calculate all the data that is coming through or not, and if not, it can automatically scale up and run more instances of this piece. And it can do this in distributed way. So this can be two totally different machines in different places, sharing the load between them. And then another idea is that you can have a bolt that accepts some messages and then outputs even more messages to another bolt or multiple bolts. So let's say it's the same email coming in, and one of the guys is just counting emails, so updating some counter somewhere in a database, and the other guy we're trying to do spam detection. So the first bolts are about removing images from emails, removing HTML code, removing whatever things you don't want to consider when doing spam detection. Maybe translating if you don't have spam models in strange languages. Maybe making sure that the words are in proper form, lowercase, all this stuff, and it's outputting a stream of words that are ready to be analyzed in context of spammy or not spammy. And then this bolt has a model deciding which words are spammy and which words are not spammy, and which emails are spammy and which are not. So the interesting thing is every time any piece of calculation fails, there will be someone tracking which word failed, part of which email was it, and what has to be retransmitted and recalculated. So this is done for you. Then scaling is taken care for you. And you can split your calculations into steps with requiring totally different scale. So for example, first piece might require a lot of CPU and a little bit of RAM, and we can run a lot of tiny instances to do this quickly. And then the second step might be quick on CPU, but might require a lot of RAM, and you can run just a couple instances not to waste the resources here. So this would be one of the usages of Storm. Another interesting usage would be to do kind of RPC to this cluster. So you have a job that requires doing 1,000 things, and you can do 1,000 things in parallel. You can send a message to Storm, and then Storm will, the first bolt will split the message into 1,000 completely parallel tasks to be done, and then the other bolt can be task executor. It can have 100 executors and do all of those things in the same time. If anything fails, then everything will be retried. And at the end, there can be third bolt that will make sure that everything is done and let you know that everything is done. So pretty interesting idea.
Can I ask questions now?
Sure, of course.
So we know what the circles mean on bolts, right? But the circles on spout, is it partition of the data that's coming in?
Yeah, it might be partition of the data. So there is a couple more nuances, and actually two meetups ago I had an entire presentation on Storm. If you want to watch it, then bigdata.getbase.com has all the recordings, and there is a lot of more details in this. But generally, it might be partitions of data.
And do you have like any control, or where you allocate bolts, like on which machines, or like is the system smart enough to put bolts that communicate often close to each other, or can you control things like this?
Depends when you run this in the first place. So if you run this on raw machines, then I don't think you have control. I mean, the system is smart enough to use different communication channels if the sender and the receiver are on the same machine, and different when it's over network. And then you can run those processes on top of resource scheduler, for example, and you can tell the scheduler how to schedule bolts. I don't think it's that smart by default, but you can totally do this.
Yeah, but these messages are like rather small. Yeah, it's not data intensive packages. It's just like information to this.
It can be both. It can be both. It can be really information heavy, and it's not a problem as long as you can scale, right? If you have a single channel that has to take all the data through, then it doesn't make sense. If you have completely separate calculations for multiple streams, then you can send a lot of data and handle them on separate machines. So the practice is this works really well, extremely well, and we had no problems whatsoever. So it's actually surprising how good this idea is. Now we've talked about Hadoop and Storm. Let's see what do they have in common. So of course, both of them are scalable. Both of them solve the problem of you want to run a program on multiple machines and make sure that it works and doesn't fail. Both of them you can treat them as kind of operating systems. So in Hadoop, this is kind of obvious. In Storm, these bolts, these are actually programs which are internally. Storm doesn't care what do. They can do magic. They can call databases. They can calculate probability. The interesting thing for Storm is it takes messages from one guy, delivers them to another, monitors that the message gets processed, and that's all. That's the end of job of the Storm. So you can write any piece of code here, put this in, and you will get your messages delivered, and you're expected to say when you processed all the messages and what are your outputs. So having this, you can treat Storm as kind of operating system as well, which takes care of routing messages to and from your programs, and then just run your program here and rely on Storm that it will run it somewhere, provide some resources, and make sure that it runs. So it's really similar to Hadoop. And in Hadoop, you can do pretty much the same. So even with the old MapReduce framework, when you're running MapReduce is actually taking data from one place, trying to process it with your algorithm, and outputting them to disk. And the processing part, this is up to you again. So you can inject your code in there. It's called MapReduce streaming, and it can stream the data to your process through Linux pipe. Inside there, you can use whatever you want. You just stream the output, and it reads it again through Linux pipe and takes care of all the Hadoopy thing outside. So pretty much the same as Storm. Actually, they can even run on exactly the same machines under sharing exactly the same resources with the new Yarn. So what the new Yarn said was, give me a program and I will just run it on Hadoop cluster. There is actively going development of integration of Storm and Hadoop, so that you can take Storm and give it to Yarn and say, like, run this on Hadoop cluster. Whenever share the resources, whenever there is load on one, then let one run on more resources. Whenever there is load on the other, let the other run on the resources and do the smart scheduling. So that's pretty awesome, and it's actually even asking itself for putting them together and seeing how you can join them to deliver really cool features. But to understand how do we deliver the cool features, we need to take a look at the infrastructure that we have in base. So everything in base is a service. We're implementing the service-oriented architecture design. So base is. How many of you don't know what base is doing actually? No one. So let me say this quickly once again. Oh, we have one person. Cool. So base is about selling more productively, and selling means you have contacts that you sell to, you have emails that you write to your clients, you have sales process, you have deals, and the logical objects you can guess what's the connection. So we have a contact who has an email address, phone number, and there is service responsible for handling contacts. Then we have emails, and there is service responsible for emails. Then we have deals, and there is service responsible for handling deals. We have tags, and there is service responsible for tags. And there is a lot of tiny services. Every single of them has a public API. They communicate through HTTP. So they call each other's API to make sure that to communicate in general, and they do not contaminate each other's data. So if there is a tag, then you're sure it's in tag service. This is really cool because we can, for example, expose this API to clients, and clients can do direct integrations with base, and they can achieve everything that is possible in the entire base if they want to. This is clean to reason about as well, but this introduces different interesting problems. So having those services have databases, and since the services are separate, the databases are separate. Since the services talk through HTTP API, they can be in Ruby, and most of base is in Ruby, but we have Python team that is developing Python services, and some of them are in Python. We have Java team, and some of the services are in Java, and there is a lot of technologies. I won't even mention like single services that expose single HTTP API to do a single thing and are written in Go or different languages. And it's the same with the databases. So you have a service, and some service wants to talk with Redis and has its own Redis, private and not shared with anyone else, exposes HTTP API, and you can access Redis without even knowing that the Redis is somewhere behind. So there is multiple different databases and multiple different technologies on the stack. And then finally, we have our beloved users, and they are mostly using two communication channels. There is actually more. So, but first, browsers, and there is browser app written in JavaScript, which is calling the same APIs to the services as the services are calling to one another. Then there are mobiles, and mobiles are different animals. Mobiles are offline sometimes, and this is a huge problem. So when a phone is online, everything is cool. You can call the services directly and do whatever you want to do. When you're offline, you need a copy of the data. Once you have the copy of the data and you do some modifications, when you go online, you have to sync the changes to the servers, send them to services. When someone else was working on your account, and usually sales is a team, not a single person, so it's possible that two people contact the same client, for example, or two people edit the same deal. We have to decide how to merge the changes, and there is a little bit of logic Actually, there is a lot of logic involved there. Pretty interesting project, but nothing is that easy. So having all this landscape, we were thinking, how do we do big data here? We want to take users' data, not really go through and scramble the logs, but we want to take users' data and provide cool features, do machine learning directly on users' data. So the obvious place would be here. So every time any service writes something to a database, then we're in the middle, we're catching the write, and we're doing snapshot of whatever they are trying to write, and we have every single snapshot of every single row that ever was written to the database. That means if you change something, then we know what was there before because we made snapshot when you created the object, and then when you update, we create another snapshot, and then when you update again, we create another snapshot. And in this way, we're able to go through time and say, 6 months ago, this row had this and that value, and then it changed here, and then it changed here. Sounds like something really useful for machine learning. So you take a look at the deal, and you can go back in time and see exactly what happened and what those events led to, and you can learn how to predict future, for example. This is really awesome, but this is not enough. We want to know something about the users. So we want to monitor what the users are doing. If they are on the website, we want to know what they are clicking, how they are behaving. Maybe we have some hidden problems in the UI, so if we knew where they have problems and where they are trying to click, we would be able to help them. Maybe we would be able to provide them with better user experience if we knew what they are looking for up front. So we want to know how do they behave, both on web and on mobile. There is a lot of really interesting things you can do when you know what user is doing on mobile, like Google Now, for example. Imagine Google Now for sales. Really cool features, so we want to have this data. But this is still incomplete. There is one more thing, communication between the services. This is necessary for joining the data from one end and from the other end. So we know what user is clicking. We know that something happens in the database, but we don't know where did it come, which way did it come, where did it wait, how long did it wait. It's really interesting operational data, really interesting for measuring how the system is behaving, really interesting for DevOps, for resource management, for tracking when and how the system is getting imbalanced, when do we have performance problems in different places. So we can track every single problem from its beginning to its very end. And then all this data, as it's being gathered, it goes to Kafka. Kafka is message queuing system. So in case there is a huge spike of messages and we're not able to digest them in our infrastructure after Kafka, then Kafka is able to buffer all of this and then let us read the events one by one. Another really interesting system, unfortunately, we won't go that deep into how Kafka works. Let's go deeply into something else. So let's understand how the entire system works and what does it allow us to do. I have this example, really cool, one of the first things that we did after successfully implementing all this collection stuff. So we had a user saying, there is something in my data, in my database. There is tags missing. I had a deal, it had 3 tags. Now I have this deal, it doesn't have the tags, they are missing. The first thing we did is, of course, we take snapshot of every single write to the database, every single record. So we figured out which deal, where it had those tags, what were the tags. We went to the history of tags database, scrolled through history of the tags he was mentioning, and actually, yes, they were deleted. Awesome. So we had the data, we were able to restore them. But this is definitely not good enough. I mean, the problem is somewhere else, right? So let's see what else did we gather. We've seen that it was the tags service that have written this or have deleted those tags from the database, but we knew even more. We knew what all the other services were doing from the beginning to the end. So we figured out that this was actually deals service, and the deals service had a deal update, and this deal update required deleting tags from the deal, so it called tags service, which went to the database and deleted the deals. Getting interesting. But we have third piece of the puzzle. We have the user data. So we went there and we figured out that it was actually user who clicked save button on deal page, which went to deal service, which went to tags service, which deleted the tags. Awesome. we looked at the history of what was the previous clicks and how did the user get to to that place, because this wasn't actually delete button, it was save button, and we figured out that the user was double clicking, and our form after first click was sending the data, cleaning the form, and preparing new page for the user. But somehow the user managed to double click in the meantime when the form was clicked, but no new GUI was showed, so he was submitting empty form and then overwriting the tags he just created with empty form. Really cool story of debugging, and we're really proud of this. So sounds like the entire system works from beginning to the end, and we should be able to track really awesome behaviors through entire base. So let's go back to the big data stack. We start at Kafka, and then all the messages queue up on Kafka in huge queues. You can have different topics on Kafka, so you don't have to read all of this. But the first thing we do is, of course, we read all of this, and we upload this to Hadoop. Not directly. As I said before, if you're running Hadoop on Amazon, you can have two kind of hard drives. You can have the HDFS, so the virtual hard drive, which is built on top of all the physical hard drives in all the machines that you have in Hadoop. But there is a connector for S3, which is infinite hard drive with really huge guarantees and really high guarantees backed by Amazon. It's really easy to write to, it's really easy to read from, and there is actually, if you run benchmarks, there is no difference between Hadoop cluster and the actual CPUs reading from local disks versus reading from S3 disks. I guess there is really good data network, and the S3 drives are co-located with the machines, and it's really awesome. So the kind of the data locality problem doesn't exist. You run your program, it reads from S3, it's always amazingly fast. So we take all the database changes, all the API calls from services, and all the clicks from users, and we pack all of this to S3. We have our cluster, and the cluster can analyze the data. But there is another path. The other path is Storm, and Storm is listening to exactly the same exactly the same queue of events. So every single time user clicks something, there is an event on Storm. Every single time that click creates a new record in the database, there is even in Storm. And you can think of Storm as this graph. Oh, sorry. You can think of Storm as this graph of calculations that have to be made in order. They can use database while calculating something. They can output the results to a database that will be visible to user. Now, why two databases? We had this fear of Storm scaling too fast and killing the user's database with reads. And we figured out it's a really good idea to have the operational database separately for Storm for really heavy querying, and we're able to scale up the cluster without thinking like what will happen if it does 1 million requests per second, because the user is being served from separate database, and then writing to this database from Storm is queued as well, and we can kill this database if we want. So we can decide, oh, there is a huge job to be done. Let's upscale the cluster to 100 machines. On Amazon, this is just a couple clicks. If it overloads the database, then it just works slower, and we don't care. And then we downscale it. We stop paying for the servers. The data is calculated, and the user is happy. So really awesome stuff. And two more interesting arrows. So this one. This is Hadoop writing to this database, but as we said, Hadoop is not actually prepared for doing like SQL insert statements, for example. This is path of taking huge bunch of data, calculating huge bunch of statistics, for example, and writing all of this to a database into a single kind of dump, so creating the entire tables at once. And then one more interesting arrow. So some of the results that we calculate on Hadoop, they are taken as they are, for example, statistical models, and plugged into Storm for dealing with real-time events. So we do really heavy lifting, preparing, for example, some statistical model, and then we're taking the model as it is ready and use it to stream single events through it and get the results of the model immediately. Let me explain all of this once again on a couple example projects that we did before. So first one would be debugging. And debugging, this is exactly the story I told you. So we just gathered all the data and made sure all the data is on Kafka. We uploaded all the data to S3. And the tricky part of the debugging was making sure that all the data is connectable somehow. So it's not that easy to say which click caused which write to the database. And there is a lot of logic involved in that, passing the token mostly. So every time you click something, your click gets unique ID, which is passed through first through the unique ID is generated in the browser, then it's passed with every single API call across the services, and then it's stored in the database as the reason of creating every single row in the database. And then gathering all the data here and sending it to the cluster, I guess it's this slide, yeah. Sending all of it to S3 and then being able to load this into one huge processing machine. This allows us to query the data in any way we want. So for this debugging, we used Hive. Hive is actually comes with Hadoop almost out of the box. So this is like the easiest, and probably one of the most crappy tools that you can use. But it's still really powerful, and it allows you to write SQL code that can query the data stored in files, like raw files on file system, not indexed, no nothing. Just because Hadoop is able to take all the data and just heavy lift all the data, go through your query and apply it to every single row, select whatever you want to select, join everything with everything, reject whatever you don't want to see, and then you get your result. So this debugging session took almost half an hour, like running this query took almost half an hour, even though we didn't have that much data yet. But for one-off debugging, this was really cool. And we were able to solve the user's problem in half an hour, which is probably much faster than any debugging done by hand. Now, this is, of course, not enough, and we definitely want to improve this. Finally, we would like to have a tool for engineers debugging the system, and maybe even support for restoring the data for the user, for being able to help the user figure out what's going on the account, who is deleting the data, what happened with my data. This is the usual problem, and we can totally answer those questions. So sounds like a really good way, and sounds like a great place for improvement. The second thing we do, and the second path we go through, is reporting. So in Base, we have two types of reporting. The first one is the standard reporting. So metrics, like sometimes you can see on the screen, these are actually served from somewhere else, but standard stuff. This many users are logged in, that many emails came through Base, maybe some A/B testing, like those users clicked this button, these users clicked that button. So stuff that we don't care about really exact numbers that much, and stuff that we can pretty freely throw out and build this again. So if we lose like half an hour of who clicked where, then on the metric we don't care that much. In the debugging infrastructure we do care, but here on a report we don't care. But there is another type of reports in Base. So Base is used for sales, and Base is used for running sales teams. And then reporting there means how much money did I earn, how good this and that person performed, how is my marketing strategy, how does my marketing strategy works, which means money of the user, and money of the user. So no mistake is allowed, no data loss is allowed, and this is really where Storm is so powerful. So having all the data from all the databases coming to Kafka, Storm guarantees that every single event will be processed. So the topology sitting here, for simple reports, there are really simple topologies that just count deals or count number of something, whatever you want to count, and then outputs this to the database, and then the user observing the report and refreshing the page can see the report change or being drawn as the events are streaming through the system. So multiple people are clicking through Base, multiple events are coming through Storm. Storm is updating the report and drawing it in real time. Everything works flawlessly. There is a tiny problem if you're trying to do a report on two related objects. So you want to figure out, For example, how long does it take for the sales reps to write an email to new customer? And then based on this, you might want to ask, how does it influence the win and lose ratio of the deals? So does it make sense to answer to the client within first minutes or hours and then put a lot of effort into going to clients fast, or up to 3 days, it doesn't matter. So with reporting like this, we have multiple objects that we want to join, like the contact object and the deal object. And then Storm is totally not built for this. Storm says there is event and its email was sent. There is nothing about the contact coming through Storm in this moment. So that's when the second database is coming really handy. And we have to store some data and some metadata for fetching when we want to pair the objects. It's worth noting that this is eventual consistency system. So even if base doesn't allow you to send email to a contact that doesn't exist, you cannot assume that when you receive the events, they will come in exactly this order. So you cannot assume that if you have an email, the contact was already created. It's possible for Storm that it decided to, for example, restart some of your calculation nodes in some other places, and your events will be streamed in different order than originally arriving in Storm. So you need to be prepared for situations like this is an email, but you have to wait a while for the contact to arrive because it was lost during rescheduling, and it will be resent, but in some time. So this database is really necessary for joining any two types of data reliably. The third and really interesting project is email analysis. So what we do is we're trying to automatically analyze emails that are going through base in a way similar to spam filters, but we're not detecting the spamminess. We're detecting how positive or negative the deal is going. So if the user says, yes, I want to buy your product, it's really good. Excuse me, it's a really good signal, and you probably want to contact the user, contact your client as soon as possible. If the user says, no, thank you, I'm interested, you can probably skip on this guy, unless this is a deal worth $1 million, and then you should probably call him immediately and get all the alerts possible. So pretty interesting feature, and requires a lot of infrastructure to achieve this. So the first thing that we do is we take all the emails and all the deals, upload them to S3 with the history of what was happening in there. And then in Hadoop, we can read the history and we can see, okay, this email arrived, and then 5 minutes later, the deal was won. That means the email was really good. Or we can go through history and see that this email arrived and then the deal was lost, and that means the email was bad. So going through the history, we can run a big job that extracts the history of all the positive deals and emails and history of all the negative deals and emails, then processing those emails. This is still a huge job. So removing HTML tags, taking care of the languages, then learning based on that. If you want to run machine learning that learns on the entire history of all the accounts in base, then Hadoop is definitely an awesome place to do this, and Hadoop has all the means necessary, so access to all of the history of the data that you want to analyze. But once you're done and you have a model that is able to score an email, then you probably don't want to do this on Hadoop, because the users would have to wait for the entire learning and scoring process to see the result, and this cannot take like half an hour. So we're taking the result of whatever Hadoop learned, so the statistical model, and we're putting the statistical model as one of the nodes in Storm. And now every email that comes to base goes through Storm as well and gets scored inside Storm. Storm doesn't need to join any data or access any other database, so can write the result directly to the database that the user will be able to read the result from. And then one more, and actually the most complex project that we're working on. The difference, there are two differences. The bottom one is, so yeah, forecasting. What's forecasting in the first place? It's answering the question of how much is my company going to earn next month based on everything that we did up until now. And there are many dimensions of this problem. So you can ask, for a single deal, you can ask, will I close it this month or next month? If next month, then it doesn't count because I'm not going to receive my money for this deal, so it doesn't count. You can ask, what's the probability that I will win this deal or lose this deal? You can ask how many deals how many new clients will come and how many new clients will be interested in my product. You can ask how much will they be willing to pay, and if they said they have 100 users, they will be willing to buy a license for all the 100, or will they want to start small and then build up? So all of those questions, they are really tricky and require lot of machine learning and lot of processing power to tackle anyhow. Yes, once again, the differences from email analysis. We have this the help database here for Storm to be able to join multiple streams of data, so we can score deals based on emails that came and are related, based on tags, based on contacts, and based on any other type of data that is going through the system. And the really interesting arrow is from Hadoop cluster directly to the database here. So what happens once we have the statistical model that is scoring the deals and we decide to build a new one? So we find a better algorithm, we tweak it somehow, we gather some feedback from users, and we want to build a new version of the same algorithm that will score the same deals, just better. We probably don't want to go through every single deal in base and rescore it again. We probably want to run a huge powerful Hadoop and use the entire cluster to rescore all the deals in the same time, to be able to generate a copy of this database from Hadoop and just push it here and overwrite whatever was there, whatever result was there from the previous old model. And of course, take the new model, put it to Storm, and let Storm score the new coming deals and update the scores for the old deals based on whatever is happening around them.
So can I have a question?
Yeah.
Are you doing separate forecasts for separate users, or you're like making one common forecast?
No, we're making separate forecasts for different users, and then one forecast. This is sum of lot of predictions and sum of lot of models. So you can model every single of those variables separately. You can look at, for example, segment of the market that the user is operating in and try to fit model better for big customers or better for small customers. You can use plenty of signals.
Yeah, and are you validating how they are performing?
Yeah. Yes, we are. So this is all part of Hadoop. So when we're building model, this happens on the cluster, and we're looking at all the historical data, doing all the tests and training the model. And once the model is trained and we're really happy with the result, we go with overwriting the database with the new scores and uploading new model to Storm. Yeah. So we can roll back time and see the entire system state a couple days ago. So we can roll back a month back and do predictions for next month, right? Now, some of the decisions that we made and some of the learning. The first thing we were really strong on was collecting all the data. So it doesn't matter if it's users click, if it's a tag in the database, if it's a comment, if it's API call, we're collecting absolutely everything. And this allows us to reason about base as an entire system, and this allows us to reason about data in the databases as an output of some actions of some users with some traits, with some habits and some liking and some not liking in the front ends. So we can profile both users and see what happens with their deals, what happens with their emails. This allows us to go through entire stack. So this was definitely a great decision, given that you're able to actually join the data. So from the beginning to the end, there has to be this unique ID of a click or of every single interaction that user does, and it cannot be lost. It has to be stored in every single place if you want to be able to cross-join all the data across the entire system. The second thing is put all the data in one place. And this is both putting everything to Kafka and not thinking a lot, is it a click, or is it a record in the database, or is it API call? Everything goes to Kafka, which means everything is streaming past the Storm cluster, and it's really easy to insert a piece of code that you want to have all the data available. They are passing by. And then exactly the same goes for the cluster. So if you put all the data into the cluster, including historical data, you can virtually do whatever you want, and there is no limitations. So definitely a good strategy. Then we're trying to build platform for engineers to use all of this. So we figured out that we have all those great technologies. We started bragging about this in the company, and then we've seen a lot of people coming by and saying, hey, you have this Storm thingy, and if I write this function, it will be executed how many times it's needed, and given all the data needed, right, and rescheduled whenever it fails. And if it fails, I don't have to care, because like this is going to take care of itself, and we want to do this. So when you're doing big data, expect people to want to use big data, which was a surprise for us. Definitely build platform, write documentation from day one, and explain how to do things, how to debug things. This is definitely not obvious stuff, but it's really powerful. And looking from high level, this is just another way of running a program just in a different place. So definitely good idea, just needs to be executed well. And the final thing to do is have the same code on Hadoop and Storm. So every time we're analyzing email content, we would like to take exactly the same function in exactly the same language and apply it by Hadoop to all the emails or all the historical data, and by Storm to the new data, because if you look at it at some level, it's exactly the same stuff, right? Just in one place you're looking at a single email, in the other place you're looking at a bunch of emails, but it's exactly the same code. So it's definitely worth investing some time and setting up infrastructure to run the same code here and there. We tried, it's not that difficult. So both Hadoop and Storm allow you to run any programs anywhere. But there is a lot of quirks, and we didn't do this at the very beginning, and now it's pretty difficult to get to the place that we have exactly the same code in both places. The code is diverging, and we see some problems related to this. Interesting idea for this problem that didn't exist when we were building the infrastructure seems to be Spark. So Spark and Spark streaming, these are two technologies with the idea of running on Hadoop with batch data and running on Hadoop with streaming data, but with exactly the same code. And this is supported natively. So this sounds like a great solution to the problem. So to sum this up, Hadoop is a great animal. It's just a bit slower and a bit bulky. And then Storm is a great abstraction that adds to the places that Hadoop is lacking. With both of them, you can do the heavy lifting, so analyze the history of all the data, train models, and do the heavy calculation. And with Storm, you can use the results of what you've learned in Hadoop, apply this to the user's data in real time as it's passing by, and then show the user the results in a matter of seconds. Questions?
You said you were going to talk about bad decisions too.
Did I? Well, we make no mistakes. No, definitely. So I started with the idea of decisions, but I put it in the way of advices. But as you see, we didn't start with writing the same code here and there. So this was a bad decision, and we should definitely do this. The platform was a bad decision as well. So we should start with training for everyone, with supporting the infrastructure correctly as it was being born. And as more features were added, we would have testers that would use it immediately, tell us what features are important, and we would have much more impact on the developers and on their productivity, and then on the users. Right now we're in this problem that many people come to us and ask us, how can we use this awesome stuff? And we say, well, we cannot support you, we're working on something else, there is not enough capacity, we cannot help you with your stuff, so either go and educate yourself or come back in a couple months. So this should be done from the very beginning. but it will be fixed. Any more questions?
You were saying about these programming languages across the platform, you're using quite a lot of them. Isn't that an issue of some sort? I mean, you know, to support it later on.
You're talking about base services or the stuff you can run in Hadoop and Storm?
Well, I guess you were talking about base services in terms of main language.
It's really awesome idea. So having normal HTTP interfaces, you don't actually care what's behind. So from the perspective of someone writing Python code, you don't actually care if the API you call is in Java or in Ruby or in whatever. It's much easier to find great people in many languages. It's much easier to provide with opportunity of like changing inside the company. So if you don't like what you're doing, we probably have another position in different place, doing different things, working with different technologies. So it's a lot of opportunities. It is a kind of a problem for projects like the collection. So we have to go and integrate with every single technology separately. So we have to write for example, the API tracking code. This is written in Ruby. It's not written in Java, for example, because we didn't write it yet, and it has to be written in Java separately, and then Python separately, and then other languages separately again.
On the whole, you're saying it's worth it.
It's definitely worth it.
I have a question. From the dashboard, I can see that we have like 140 terabytes of data. How much of this is, how much of this is data? How much of the data is like real customer data and not like the exhaust of the system itself?
So you can talk about data and data. This is really aggregate number. So this includes, is it 1 terabyte only?
140 terabytes.
Oh yeah, 140 terabytes, but local disk storage, for example, is 7 terabytes. So there is a single answer to this, like I have this and that 140 terabytes data. This is usually bullshit because you have to multiply this by value. So if I tell you that 100 gigs of this or 100 terabytes of this is backups, it's worthless. Then logs, not that worthless, but still. Then information about the operations within base. This is like huge piece of data. But the value is, well, sometimes it's useful, sometimes it's useful for DevOps, but the real pay data, this is actually what's happening inside MySQL database, and this is what's happening on the mobile devices and on the web when user is using application. So the question of like how many gigabytes you have doesn't make sense. The question is how much value do you have in those gigabytes?
Yeah, like talking about databases, are you using like mostly relational ones or?
For the services, this is mostly MySQL. Redis for some fast and easy, like caching-like solutions. We're using Cassandra we were using Cassandra in one of the big data applications. Now it's decommissioned, but we're looking into reviving it again. We're looking into Amazon Redshift as a database that we would use for querying really big data. I don't know. Do we have more databases? Elasticsearch. Oh yeah, Elasticsearch. Really interesting database. Great for text searching and great for data aggregation. Memcache, kind of database.
Yeah, the stuff you were talking about, collecting the data from the operating system, the data comparing blockchain, like it's similar with what we're dealing with in classical warehousing, but then you just go with relational systems.
So we don't care that much about the relations. If we want to restore the relations later, then we can do this. The only thing we care is there is a guy named John Doe, and he's created right now. And then 10 minutes later, someone comes and says, "This is not John Doe. This is John Doe," for example. So we want to know that there was a record in this time saying John Doe, and it was created by this guy, and then the entire tree of like whatever happened in the same time. And then we want to know about the update, and we don't care if the John Doe is related to some other table because we have complete history of the other table as well. So we can tell you this guy was related, for example, this tag was applied to John from different service, and then the tag was deleted and it's not applied anymore, and now it's not. So asking any question, you need to take a look at given point in time because everything is changing.
Anything can changes about the object when you just make a copy.
We make a full copy. One more?
Do you have any anonymization in place on this whole workflow?
Not yet. So we're not exposing this data to any external researchers or any people outside of the base. And then inside of the base, big data team has access to the big data, right? And we're doing our best to track this, but we're not on the level of like corporate policy and allowing random people to access the data and having to apply this. But we're not gathering. So what we're gathering, we're not gathering your personal web searches. We're not gathering information about where you went for a walk. We're gathering the information that businesses give us to help them with their sales process. So we're gathering information like this user changed the name of this contact at this time from this and that page on the website. So this is not something that would invade your privacy. This is actually the other way around. Companies are trusting us with the data and paying us to give them insights from this data and to let them be more productive at work.
When Hadoop is running to refine the models, does it happen all the time in a loop?
It happens once a day.
Online the response, but with a delay, or you just request that, look at the results and decide to apply them to that processing on my story?
The training happens every day because every day, so depends on the project again. Some of the projects are just retrained every day. First to make sure that the entire pipeline still works and there is nothing broken. Then if we're training on last 6 months of data, for example, and you have one more day available, then it doesn't change the results that much that we would really have to sit there and manually apply every single update. With some projects, we're gathering feedback. So for example, if we say that with the email project, if we say the email was negative and it was actually positive, you can give us feedback like with spam and say this is not spam or this is a positive email, and then we want to incorporate those things into the lab as fast as possible, but still this happens once every night.
Can you give us some examples of the insights that you give back to the clients that help them? Like you should answer emails very quickly, or
so there was the really cool thing about Base is we're using Base to sell Base. So we have our internal sales team that is using Base, and we have our friends sitting at Base 8 hours a day and telling us what they are using. So there was this idea of how important this is to contact a new customer immediately, and there was this idea if you create an account in Base and put in your credit card and you want to have let's say more than 10 users, then some of our sales get notification immediately that there is a new client and they should contact them as soon as possible. So the idea is you're clicking through Base and someone is calling you, and this is really awesome experience. Yeah, they explain you exactly what you need and yeah, it should work. And for validating of this, we built one of the reports that I mentioned before. So for every new contact and for every new deal, we're looking at emails, at calls and SMS messages. We're tracking how quickly did you respond, and we're providing you a report immediately. So if you want to implement policy of contacting the customers quickly, then your line should go down to like 5 minutes and then stay there. And then another layer to this report is the outcome of those deals. So whether you won the deal or lost the deal based on how quickly you answered. So for 0 to 5 minutes, you have, for example, 10% win ratio. For 5 minutes to 20 minutes, you have 7% win ratio, and you should see a like optimal bump of how quickly you should contact the customers. And the really cool insight was if you contact someone within 5 minutes of creating the account, it's super creepy and they don't want to talk to you. Hello. But yeah, less than an hour has really good results. So we implemented this. We released this first for our sales account. They found it really useful. They implemented it, and we released it for all the other users, and now it's available for everyone. There is blog of describing all of our features and documentation, or just go to the product. You can start a free account and see how it works. Send yourself an oh, unfortunately the email thing doesn't work yet. It's not released. It's internal for now, so you cannot see the email scoring stuff yet. But it's going to be there soon.
Is someone going to call me in an hour after I set up this account?
We're not doing this anymore. Probably, but it's still possible. I mean, the sales team is really awesome, and they are trying to do their best, so it's possible. One more.
Credit score first.
Oh yeah, yeah. If you claim to be Microsoft and you turn out to be Microsoft, then they will call you immediately. Last question.
Yeah. So when it comes to so-called event-oriented side of your architecture, you've mentioned that you're kind of interested to record everything that the client do on the client side. You especially mentioned that you want to assign a unique token to every button click, for example. My question is, do you store that data in form of logs, for example, or do you store as the records in a relational database, or use some form of NoSQL solution for this? Maybe I missed that. Or
so let me go back to the infrastructure. Where is it? Yeah, so the token is generated every time you click something on a browser or every time you click something on a mobile device. And then this token is attached to the request that you do. So if you click a button and nothing happens, then we're buffering those clicks that you have and sending them periodically to a service that is sending it directly to Kafka. And if your click causes an API request, for example, then one of the request headers is the interaction ID, and then this gets carried along the line. So we're catching all the requests here, sending to our infrastructure. So we have this once, then it travels through the services, and we catch this every time it jumps between the services and send it to us again, and then it goes to the database, and every save to the database is carrying this interaction ID as well, and we're storing this again. So we have at every single step we're catching whatever is happening with your interaction ID, and at the beginning when you're generating this, there is one more event sent directly to our infrastructure saying like this guy clicked this button and this is the ID.
Yeah, I think that's clear, but my question was actually about the form you store the actual data about this event, I mean the token. So for example, is it the record in the relational database? It's information in logs that you mine them, or?
No, it goes to Kafka and goes straight to S3. There is no intermediate storage, and then it goes through Storm as well. So you can for example, if you want.
For example, store it as the records in S3 storage.
Yeah.
Maybe just one. The database that the user is querying. What is that? Elasticsearch.
Elasticsearch is really awesome for aggregation, and this was mostly for the reports. Yeah, if you want to aggregate and let people filter by some fields and then aggregate values in other fields, then Elasticsearch proves to be really awesome database. So that's it. I guess we don't have that much time left, so I guess I have a couple slides left on the other hand. Questions, of course. There is one more thing. If you find this fun and challenging, visit bigdata.getbase.com. There are recordings of the previous data KRK meetups, a couple articles about our team. There is this careers button, so not mentioning and not being that obvious, but definitely visit this website or come talk to us with the beer. Thank you.